maybe that's for now for the question and answer section. There is also one question here, but we will maybe we will answer it after the next presentation. Maybe you could continue your presentation, Pak Devy.
Okay. There is one station. I will just answer this very fast because said only one side, as in the case of Merapi. It depends on the difficulty of the volcano. So if you see that Merapi, the summit is here, and you see that all the surrounding of the Merapi is covered by the instruments. So we have like more than 70 70 stations around. So and this is enough to get many information from inside Merapi. But for other cases, if you have we have like difficulty to go to some side of the volcano, then we have nothing to do, because sometimes, for example, we have like lava flow going there, and then we don't have stations here, but it will risk our lives if we want to install it here. Then it's nothing to do. We don't have to install it, or we don't have to install it there, because ideally we must have stations surrounding the volcano, but in reality, sometimes you will face like a very steep environment, and it is difficult to install there. Then we have to deal with that. So we have to accept that we cannot install on that place. Okay, I will continue with the seismicity at volcanoes. Yesterday, Professor Andri have already shown you about the classification of seismic events at volcanoes. So this is what he, if you see this, wait, I'm sorry. Sorry, I lost my, okay. So there are mainly high frequency volcanic events, low frequency, hybrids, explosion quake, and volcanic tremor. So Minakami is one of the first seismologists who classify volcanic events. At that time, there was only two types of events, A-type and B-type events. And for the superficial activity, volcanic tremor is classified as volcanic tremor. And also the surface activity, it's called the explosion quake. So the A-type is the high frequency event, and B-type is low frequency events. And later on, later in 1979, made another classification that the high frequency events are called volcanotectonic. And then for the low frequency, it's called volcanic. So if you say volcanic earthquakes, it means that that's low frequency earthquakes in the term of latter. And hybrid is a medium frequency that was said by latter. And also the explosion quake is volcanic explosion, volcanic tremor is volcanic tremor. So the Alaskan Volcano Observatory in the US made another distinction. So that's the first one is the high frequency events. It's called the volcanotectonic. The low frequency events is called the long period events. Hybrid is the hybrid, and explosion, and tremor, and tremor. So other names you can find like the short period earthquake if it is a high frequency, and long coda event or tornado, and mixed and the hybrid or the mixed frequency or multi-phase in Merapi, for example. And harmonic tremor for the volcanic tremor, there are harmonic tremor and also spasmodic tremor. So what are these events? You may wonder what are these events. So these are the source processes. So for the high frequency or the volcanotectonic events, it is mainly caused by the brittle or shear failure or slip-on faults. It has similar waveform. If you see in it, it's like tectonic earthquakes, but the difference is only in the magnitude. It is lower, mostly below 3. But prior to a large eruption, you may have more than magnitude 3. And also the difference is also in the term of the pattern. Because in tectonic earthquakes, you have swarm, you have main shock and aftershock sequence. But in volcanic areas, mostly you have swarm. Swarm, you don't have like main shock and aftershock sequence. You have like a irregularly increasing and decreasing pattern of amplitude. And also, and then the second one is low frequency or long period tornado events. It's caused by the fluid pressurizations, like bubble formation and collapse, and also by shear failure or tensile failure of the rock, or nonlinear flow processes that occur at very shallow depth. So mostly around hundreds of meters below the crater surface. For the hybrid events, that's the mix between high frequency events and low frequency events. Mixed, what I mean with mixed is that it has the onset of high frequency events and then coda of low frequency. So the process, it may be in the form of earthquake, high frequency earthquake occurring adjacent to a fluid filled cavity and setting it into an oscillation. So this oscillation is what we see on the coda, and the earthquake in the beginning is what we see in the onset. So, and the last is volcanic tremor. So the volcanic tremor is pressure fluctuations of the gassing magma multiple. You can see all these at McNutt and Broman in 2015. So, but to give you a better illustration, so I will use White and McCausland publication in 2019 about process-based model of pre-eruptive seismicity at volcanoes. You see on this picture, there is numbering 1, 2, 3, and 4. 1, 2, there are 2, 2, and then 3 and 4. We will talk about this. What is 1, 2, 3, and 4? So the first stage is seismicity that is associated with magma rising from a lower crustal storage region. And then as magma is coming up, then the seismicity associated with that magma already in upper magma storage region, it will cause seismicity nearby. So that's the second stage here. And then the third stage is the seismicity that associated with magma moving upwards from the upper magma storage from here to the surface and starting to move across a pressure barrier between the lithostatic and hydrostatic pressure. So you see the plastic and brittle zone that I showed you in the first image, aerial photo. It is this. So when it breaks this, it will interact with hydrothermal system if you have hydrothermal system of the volcano, and then it will give you another signature of seismicity. And the fourth step is the last step. So it's a very shallow seismicity that is associated with the final ascent before the magma reach the surface. So we will talk about which these 4 types of seismicity. I will add one, surface stage seismicity. So it is the surface activity. So seismicity accompanying the eruptive or surface activities. Surface activities can be in the form of the gassing or gas emission, and also the eruption. So, and we will talk about the first stage now. Okay, so this is the first stage. Seismicity associated with magma rising from a lower crustal storage region. It is more than 15 kilometers beneath the volcano. So what type of earthquake? This is like the deep low frequency. It is called the deep low frequency events. So these events are proximal. Proximal means that it is beneath the volcano. So proximal is beneath the volcano. And it has low frequency content of lower than 5 Hertz mostly, and recorded at several near field stations. So even if this is a low frequency event, and but as it is deep, mostly it will be recorded by many stations around the volcano. But in reality, in prospective analysis, if you are monitoring a volcano, it is difficult to identify this kind of signal. So, and most often it's rarely observed. But if you manage to detect these events, it may later include a deep LF tremor. So from this small or this short duration deep LF, it may become longer and forming LF tremor or deep VTs afterwards. So, but this is difficult. Once again, it is difficult to observe. So maybe like you will not record this at all at your station. That's a bigger possibility. But this one is a record from Sinabu in 2014. So it was recorded by several stations, and it is a deep low frequency. So remember, proximal means that it is beneath the volcano, beneath the volcanic endospheric. Okay, now we move to the second stage. So the second stage is the seismicity associated with the magma intruding into an upper magma storage region. So at this stage, normally is the earliest stage that we manage to record or we manage to detect. This is in the form, normally in the form of distal VT. So what's the difference between proximal and distal VT? So distal means that it is not exactly beneath the volcanic edifice. It may be farther, can be like tens of kilometers far away from the volcano. And you think that that was not related to the volcano, but in fact, that's related to the volcano. So, and what the characteristic of this event, you see that the P and S wave is very impulsive and distinct. You can make difference between the P wave and S wave. So, and it has, you see on the right side on this spectrogram, you see the high frequency content of more than 5 Hertz. Normally, for a high frequency event, it has like 5 to 15 Hertz in dominant frequency. And normally for this kind of activity, it can be it will be recorded at several nearby or near field stations. And at most volcanoes, the appearance or the occurrence of distal VT is observed as the first signature prior to an eruption. So if you have many VTs before on dormant volcanoes, then you have to be careful, because this distal VT may inform you something is happening inside the volcano. Maybe there is magma trying to intrude and to reach the surface. But we not only distal VT, we need another signals to clearly see if the volcano is going to erupt or not. Then we need the third stage. So the third stage, you see that it's shallower. So the seismicity in this region is associated with magma moving upwards from the upper magma storage, from here, to the surface, and it is starting to move across a pressure barrier between the lithostatic and hygrostatic pressures. So when the plastic and brittle zones, the brittle ductile transitions passed, then you will have another type of seismicity. And this type of seismicity that we are talking about. This is when the magma can be like the fluids or the heat from the magma interact with the hydrothermal system. It will provide another signals. And another signals can be in the form of proximal VTs. So unlike distal VTs, proximal VTs here is located just beneath the volcano. So just beneath the volcano. So different with the distal, which is not exactly beneath the volcano. So the proximal and shallow volcanotectonics, it occurs under the volcano. and it has like impulsive arrival signal, but sometimes it has obscure P and S wave onsets. So it's sometimes you cannot distinguish between the P and S wave. It may be merged or you cannot see it clearly. But if you have a farther station, or you have a farther station, you may have you may see the P and S wave arrivals in other stations. So yeah, if you have a good seismic networks, you could still see the P and S wave arrival times. And the good network means that you have a dense network within like 30 kilometers or 20 kilometers, something like that. And it has high frequency content, as I said before. It's similar. It's 5 to 15 hertz frequency. And still in the third, no, it's a fourth stage. Okay, it's a mistake. Sorry. So it's a fourth stage. So the fourth stage is the one that is really near to the surface. So in the beginning, we have like tornado. I think I have this. Sorry, I need to check because I normally have the. Okay. 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 I think I have misplaced the slides. I would like to stop share first. I would change this because this is okay. Okay. The third stage is here. So the type of seismicity that we have will be proximal pitches that I have told you before. And afterwards, we will have like something like hybrid or LF events. So the hybrid is, it has two regions of energy, so spectral energy. So it has the onset of high frequency events, as you see on the screen here. I will do the spotlight here. So you see that the onset is higher frequency, but then followed by the low frequency. That's the hybrid events. So the hybrid events is an event also located beneath the volcanic edifice and relatively shallow. So, and the other one is the low frequency events. Unlike the other events, this event has an emergent P wave arrival. So it's not impulsive like the volcanotectonic events, but it has emergent P waves and lack of distinct S waves. So the low frequency content is between 1 to 5 hertz, but most of the time it is very common in the world that we will have like 2 to 3 hertz. I don't know why, but on Indonesian volcanoes and other volcanoes, most common around 2 to 3 hertz. And this is related to the dimension of the cracks or the conduit or the crack of the conduit dimensions. So while the frequency is related to the dimension of the cracks or the conduit, the changes in frequency may indicate the changes in the cracks in the conduit. And thus, it indicates the changes in the pressurization, the fluid pressurization in the shallow part of the volcano. So, and then the fourth stage is the shallower one, let us say. So shallower than the LPs, LP or the tornado it is most likely you will most likely have these events shallower than 1.5 kilometers. At some volcanoes, like what I have I have worked on, it is in around hundreds of meters below the crater. So you see, the waveform is characterized by a screw-like signals with slow decaying coda. So it's like a screw, and the low frequency content. So the dominant frequency content is below 5, so between 1 and 5. But the one unique things about this event is that it has sharp frequency peak. So you see that this is very sharp, 1, then 2, 3, 4, and regularly spaced. You see that the first one is around 2 to 3 here, and then the second one, and then the third one, and then the fourth one. It makes a harmonic signal with regularly spaced spectral energy. So, and if that events become longer and longer, it will form a longer event, which is called the harmonic tremor. So the harmonic tremor is looking like this. You see that in fact, seismologists, volcano seismologists say that if it is still lower than 1 minute, then it considered as long period or event. But if it is more than 60 seconds, sorry, if I say 60 minutes, but 60 seconds. If it is less than 60 seconds, we say that long period events. But if it's more than 60 seconds, we may call it tremor. And this kind of thing is the harmonic tremor. You can see that this is you can see the harmonic order. The frequency order is it's very regularly spaced. So you see that this is relatively uniform and low frequency content, 1.56, and sharp frequency peak. See that the frequency peak is very sharp at several frequency peaks. And fourth state also that we would probably see is another type of tremor. It is called a spasmodic tremor or spasmodic burst. But you have to make difference between the low frequency tremor, like the harmonic tremor, with this spasmodic burst. Because spasmodic burst, it is not the it's like for the harmonic tremor, it's like the compilations or the burst of low frequency events. But in spasmodic tremor, it's the burst of VT events. So it's the burst of VT events, but they are all same tremor. But the difference is that for these events, spasmodic, it has higher frequency content. So mostly 5 to 10 hertz. So that's so you see that it's pulsating and irregular appearance. It's very different with the harmonic tremor. Okay, and then the surface stage is seismically accompanying eruptive or surface activities. It can be in the form of emission. If you how's the eruption looks like? It's like the bigger version of the emission. So you see that I only show you the example of emission, because if I showed you the example of explosion, then all of this spectrogram will be red. So so just to show you that it's a mixed frequency, you don't have distinct dominant frequency in the emission or explosion signals, and also with the rockfall as well. So the rockfall, for example, like if there is a pyroclastic flow, you can also record this kind of events, and it may be long. So for the emission, it takes like seconds of it takes like 35 seconds or 60 seconds. But for eruption, big eruption, it will form a very continuous signals, and it's like a continuous tremor with irregular amplitudes and it can last for hours or for many hours. And for rockfall, it may be like in minutes. It depends on how long the rockfalls or the pyroclastic flows moving. So in short, I will show you the processes from before the eruption to the eruption in this image. So this is the first stage. You have a crystallized magma, so it's not moving at that time, but yeah, and then it starts moving, and then it's going up, and when it's hit, when it was it was when it was here moving, you can already have like brittle failure around the volcano that creates the distal VT earthquakes at this stage. So you may see some earthquakes, but not just beneath your volcano, but outside of the volcano. So, and then after this, when it breaks the transition seal here, the seal between the brittle zone and plastic zone, it will give another seismic signals, which is the proximal VT earthquakes. It's already beneath the volcano, at the volcanic edifice. So this is can be like you see the dots here. That can be the source of the events. And then after this, so as the heat from magma is going up, find its way, it will make a vapor zone right there, and then at certain point, it will accumulate and will show a degassing activity. So if your volcano, for example, normally do not degas, then if there is a degassing, it means that there is already this kind of process that could, that could be this kind of process that happens. So if your volcano always in degassing mode, then if it is degassing, then it's this kind of process is a background process. So, and then when magma is moving, here you see that magma is still there, but then it's moving up, and in a matter of maybe hours, when it interacts with water, it will provide an ash eruption and phreatomagmatic eruptions. So that's the story of the seismicity accompanying the ascending magma before the eruptions. So I will go back here again to this image to show you the chronology leading to eruptions based on this model. So on this model, as I showed you before, but I will put this in this slide. You have deep seismicity, stage 1, distal VT seismicity, stage 2, and then the vent clearing seismicity, stage 3. It can be in the form of phreatic or phreatomagmatic eruptions, accompanying the shallow VT, accompanying the LF tremors. There could be already some phreatic explosion. And then the repetitive seismicity, the stage 4, like I said, the repetitive, like the harmonic tremor, the repetitive hybrid events, and also the spasmodic burst. That's a repetitive seismicity. So, seeing this sequence, we will see on the case on other volcanoes, on different volcanoes. So as you see here, for example, in Kazatochi, in 2008, the earliest signals or the earliest signature, as you've seen, is in, oh, sorry, it is here, blue color. It means that in this stage, the first signature, seismic signals that is recorded in Kazatochi was distal VT. So, and then it is increasing over time and reach a maximum magnitude of 5.8 before the explosions then happen here. So before the explosions happen here, you see that, so this is the blue line. So it means that the distal VT seismicity here. And then it's has transitioned to the green one, to this activity, until the eruptions. And then it is moving then again to here. Yeah. So that's the red one is the magmatic eruption. See? So purple, you have to recognize the color. The purple, the blue, the green, orange, and red. So you can see that. And also in Cholo, volcano in Indonesia in 1983, there was a big eruption of VEI 3 to 4. So you see that the final product is VEI 4. And then you see it was beginning, the beginning was swarm of earthquakes, distal VT. So distal VT, and then it reached a magnitude of 5.5. And then it was followed by VEI3 eruptions, which is increasing over time, and then concluded by the largest eruption of VEI4. And also for other volcanoes, it's almost similar that in the beginning of the crisis, it will always be started by distal or volcanotectonic events. Except, but it's not always, except for some examples like Syahbana here. You see the Syahbana, they detected the first deep seismicity, but it shortcut the second stage. So it moved directly to the third stage, and then eruptions, and then back to stage 1, and then stage 2, stage 3, and then stage eruption stage. So if you see like this, it is not, even if we have already this kind of model, you don't always have the ideal sequence. It can, but most often it will be like this, most often, but not always. For example, the good example, like in Cholo and Mount St. Helens, it shows like you see that you have like the second stage, the third stage, fourth stage, and then fifth stage. That's the example from Kalu 2007. So you can see the progression of seismicity over time before the eruptions. So, and the next one is an example from other volcanoes in Galeras, for example. You see that this is the progression of, you can see of a very long-term seismic progression from 1988 to 2014. We can see that the first stage here, see, was the distal seismicity, and then continue by the stage 3, the proximal earthquakes, band clearing seismicity, and then also the repetitive events, and also the magmatic eruptions. So so this is an example that it can happen short term or long term. So if you ask what time does it take to go from stage 1 to 2 to 3 to 4, there is no linear, there is no common duration. But yeah, so that's the difficulty that we have to handle. And then the source mechanism of the of this seismicity here, if the for example for the event, we will distinguish only the high and low frequency. So for the high frequency events, it's a volcanotectonic event. And for the low frequency events, it can be low frequency, low period, or tornado, or harmonic tremor. So the phases for the high frequency event is clear onset on P and S waves. But on the low frequency, it's ambiguous, particularly S waves. On the spectrum side, the high frequency have the a frequency range of 5 to 50. And for the low frequency, it has 0.5 to 5 hertz. And then the location, mostly the location is around the fault or around the conduit or dike for the high frequency events. And also can be spread widely in the volcanic body. So, but for the low frequency event, the location is concentrated in narrow zone, can be in a form of a conduit or crack. And the source mechanism of these events for the high frequency event, it's like the tectonic, the classical tectonic earthquakes. You have a double couple source mechanism. So it is because when the magma is moving toward the surface from depth, it may cause rock failure or slip on faults. But there is no volume change of the source. So and the and the low frequency event is the different. It is different. So it is a non-double couple. So it's the expansion or contraction, can be expand, can contract, of gas-rich fluid inside a narrow zone. So there is a volumetric change of source, and we monitor this using the low frequency events. So that I told you before, we monitor the frequency and also the Q factors of this coda of the low frequency. The low frequency, for example, like the long period events, the frequency related to the size of the cracks or the conduit, and the Q factors related to the acoustic, to the type of the type of the fluids. So, and the focal mechanism, seismicity at volcanoes, we have both. For VT earthquakes, we have like the tectonic earthquakes. It is the double couple. So you have the quadrant type. You have like you see here, and you have the double couple mechanism. But for the low frequency events, you have the same polarity. It is push or pull, and then the source types of these LF events can be in the forms of isotropic source, or tensile cracks, or cylindrical. So it depends on different volcanoes. It may differ. It's not always the same. But these are the three main source type of LF events that we recognized at the moment. And like tornado, something like that can like I have done the modeling for this tensile cracks in the tornado